Good morning. My name is Pete Pettit. I'm the founder of VGlass. I've spent my whole career in R&D, the last 30 of it in management.
It's the same sweat.
The problem that I decided to work on when I left the industrial world to go off on my own was that 3% of the world's energy is wasted due to the thermal inefficiency of today's windows. My daughter did this. So I'm going to go through these slides relatively quickly so I stay on time, but we can come back if any of you want to ask questions. The impact of vacuum glass can be tremendous. It could save, if it was rolled out through the whole market of the United States, it could save 2% of the entire amount of energy that the US uses in a year. Compared to solar, it's over 2 times what was generated in 2017. Our trademark is reminiscent of a 1910 Thermos bottle to remind us of what our job is. It's very difficult to make a Thermos bottle that is flat. It's taken 97 years. It was done by Richard Collins at the University of Sydney in the late 80s. Part of the reason it's hard is because there's a 100-mile column of air above every square foot of window. And that's the equivalent of a steel slab that's 4 feet thick. We need to keep those panes separated by at least a gap that is as thick as your hair. And so we use spacerettes to do that. Very tiny, so they're very difficult to see, but we need them. You can see the tiny spacerette. We also use foil, and we use a direct-to-glass weld, ultrasonic weld, cold welding at room temperature. We can make this in any shape using the systems that we've developed. The nice thing about vacuum glass is it actually makes the home more comfortable because the internal pane of glass is closer to room temperature. As far as applications are concerned, I want to say right at the outset that risk comes from not knowing what you're doing, according to Charlie Munger. And I don't know what I'm doing when it comes to space. I'm hoping that the NASA engineers can help me out on this. But I think solar cell interconnects are another interesting possible application. My expertise really comes down to the terrestrial window world, where I've had a lot of experience. The global market for the terrestrial window world is $40 billion a year, and the US share of that is about 20%. The market driver are really the building codes, and Energy Star has been very, very important in the driving of the building codes. Building codes will often reference the Energy Star program. By the way, R value means resistance to heat loss, and you may be comfortable with that if you've gone shopping for windows. R value is used at the consumer level. VGlass aspires to generate an R10 window. So it would be a very, very radical departure from the trajectory that we're currently on. This is a very important slide. It's very complicated, but I'm going to try to subdivide it into small chunks. First of all, we've talked about the importance of building codes and driving the end pool, the end user pool needs for good insulation. But our customer is really upstream at the insulating glass manufacturing location. So we have different sensibilities than you might be used to thinking of in the commercial market. VGlass sells technology, not glass. Our income comes from royalties and from equipment sales, that is, equipment that can't be bought on the open market today. We'll use existing routes to market because it would make no sense for us to duplicate those. The important thing for us, the hard part is not the technology. We know that works. The hard part is the cost. The cost is the important thing, and what we really have learned clearly in the last year is that we need to be competitive with dual pane, which is the current standard in the United States. Our 3 times performance premium here, if we can do 3 times better on the R value, that will allow our customers, the insulating glass makers, to charge higher margins. And their margins are pretty thin right now because window glass is a commodity. This tells you why they will be able to mark it up. A high-end wooden frame, the light might represent 20% of the manufacturing cost of that window. So if you increase the margin from a 32% markup to an 88% markup, hypothetically a 2.5 or 2.7 times increase, the pane felt by the end user is only about an 8% premium. That's a pretty reasonable premium for getting a 3x improvement in performance. VGlass is thinner. We could fit 3 of our panes on top of each other in the space used by a dual pane window. We focus on room temperature processes because we're driven by cost. And heat-based processes are just very time-consuming. To heat glass up, which is very, very dense, takes a long time and is very sensitive because it's so brittle, that takes hours to heat up and then hours to cool down. So if we can do room temperature processing like our welds, that means a huge difference in the manufacturing cost. Another example of our room temperature approach is in degassing. The vacuum gap needs to be very dry in order to deliver a long life. And you can see that heating up thermal degassing, which is as old as the light bulb days of Thomas Edison, takes a lot of time. We can cut that way down by using plasma that bombards the internals of our vacuum glass chamber with billions of tiny ball peen hammers to knock off the moisture molecules. And this map shows competition on a scale of performance, or R value, and manufacturing cost. Dual pane is our reference. That's our bogey. Triple pane costs a little bit more, not too much more, but it costs a little bit more, and it performs quite a bit better than dual pane. You might be able to get an R3.5 or R3.5 here. You might be able to get an R5 window with triple pane. The DOE goal is R10. We can do R11 according to the models that we've run, and also our testing in the lab support that. The first window that delivered R10 in the commercial space was Alpen. They delivered using a multi-cavity xenon-filled, more or less a version of the dual pane that's been expanded. But the cost is high. Vacuum glass that's on the market, that's been on the market since the late 1990s, can also generate a good R6 window, but they can't do any better because of the technology limitations of what they're using. We've found a way to break through that barrier. Also, their costs are very high because of the high temperature ovens that they use. And those ovens take a lot of electricity. So the cost of electricity is very high. VGlass is a generation 2 technology. We're using different technologies than anybody has ever used before, and in more than one part of the window process. So our value proposition is that we can deliver 3 times the performance, 2.5 times the life, with no more manufacturing cost. And the nice thing about vacuum glass to the end user is it's a green technology that is invisible, unlike solar cells, unlike windmills, which you can see and some people don't like in their backyards. You won't be able to know as you drive through your neighborhood whether somebody is using vacuum windows or not. This is our progress since our founding in 2008. In the early days, we ruled technologies out and established our philosophy. And then we started getting grant money from the federal government, NSF, DOE. So far to date, we've accumulated $1.7 million in grants. And we've just put in another proposal to DOE for another $1 million for a phase 2. During that time, we've been able to ramp up quite a bit of progress on this line. We've shown that we can get the performance. That was pretty well unknown. That's just physics. But the challenges are going to be to realize the life potential as well as the cost. And the cost is really the king. This is our commercialization plan. I've got 1.5 minutes. What we're doing here is we're spending that DOE money. Hopefully we'll get that. If not, we'll have to go to the private market and get it. But we're looking to raise $5.5 million and then another $7.8 million in order to invest in the first commercial line. And if we can start sales in about the 2021 timeframe, we could reach break even as early as the end of 2023. It ramps up pretty fast. We've got 3 pending international patents, and the beauty of our Generation 2 approach is that there are very few, if any, patents in our space. This is all Generation 1 technology, solder glass, edge sealing, and pillars. This is our board of advisors. In particular, these are mostly business partners from an angel group that I belonged to. But I've invited Bob Spindler, who's the vice president of R&D at Cardinal Glass, retired now. He's a good friend, and he's got a wealth of experience, and so he gets 3 X's. Again, I want to point out the large terrestrial impact that we could have. Not the space impact, but the terrestrial impact. So thank you very much for your attention, and I'll take questions.
How reliable is your vacuum seal?
We're currently undergoing testing at NREL. The seal has undergone 350 cycles between minus 40 degrees centigrade and plus 80 degrees centigrade 6 times per day. And out of the 4 windows we started with, one of them we cracked the glass. So that's not really a failure of the seal. I'm going to set that aside. Of the 3 remaining, one of them failed after about 60 cycles, and we needed 54 cycles to demonstrate 50 years life. So the other 2 are still going strong.
Is 80 degrees high enough for a test? I mean, say I did this in Arizona, is it going to get hotter than that?
Well, in the industry, the conventional test, the standardized test, ASTM, E2190, runs between minus 20 degrees centigrade and plus 60 degrees centigrade. So we're exceeding that on both ends.
So if you did get a leak, how easy is it to replace the glass? Or do you have to replace the whole window?
If we got a leak, you're going to have to replace the glass as you would a conventional insulating glass unit.
Do you have other benefits? What about sound isolation in the windows?
There should be sound isolation. I was just talking with a colleague at the University of Sydney the other day about this. It seems that it's not clear among the experts whether it's better or worse than conventional
But
insulated
you
glass.
haven't tested specifically.
I haven't tested it, no. There has been testing done, though.
Hi, I have a question, and I know nothing about Windows, but it seems to me that if this product was so good, why wouldn't the people that sell Windows be paying you to develop it?
We're negotiating with them to make that happen. We've just had a letter of intent signed by one very large maker, and they are going to take the rest of 2018 to think about it and do testing on our windows. And if they see that it matches their needs and doesn't have too great of a risk, then we are proposing that we'll enter into a joint development agreement that would be funded by them over the following 2 years. And that money that would come from them would be leveraged by hopefully by the $1 million from the Department of Energy in order to make the pain and the risk that the private sector would have to bear to be less.
So then why do you need us?
Because there's a need for a good $13 to $15 million total. And the industry that makes insulating glass is extremely conservative. Very, very, should I say, they squeeze a nickel because they're in a commodity market, and that's their mindset. So I'm looking for people who have vision, who understand the potential of this technology and can join with us to roll it out in a big way.
Could you give us a sense of how you're differentiated from the prior R5 vacuum glass? Why is your performance so much better than what's been done before?
That was the subject of a phase 1 DOE project that we just completed in March. And I can't reveal the secret, but the key is that the shape of the whisker or the shape of the spacerette matters a lot.
Thank you.
I was actually going to ask you about the spacerettes. So how, and this might be delving into the proprietary, but it seems to me one of the challenges here would be the cosmetics of that, and I think also the reliability of the positioning of these spacerettes. So how are they held into place? Is it just the pressure associated with the vacuum?
In the
Pinning them?
In the technology that has been on the market for 2 years, or for 2 decades, I should say, it is strictly the 1 ton per square foot that holds them in place. And we aspire to do that too. Right now we're using some adhesive just for manufacturing convenience, but we're going to get rid of that, I'm sure.
And on your picture, you had like a white dot there,
Yeah.
but the white dot was obviously a PowerPoint dot, I think, right?
Yeah.
So what does it really look like? Would I notice it if I'm looking out the window?
First of all, it's going to be, the gap is as thin as your hair. The conventional vacuum glass that's on the market uses pillars, which are really like miniature coins. If you can think about them as miniature coins, they're probably about 200 microns thick, 500 microns diameter, and they look like fly specks. When you back off about 10 feet, you can't see them, except if the background is right. With ours, we have our size, because of the advantage of the shape that we're using, our size is 25% of what a pillar is.
So this works, this is all about the spacerettes. It's not about the composition of the glass itself, so it'll work with any kind of composition of glass material.
It should, and of course, because we're so cost sensitive, we need to use the same glass that is currently used to make windows, because that's the cheapest glass. Soda lime glass is what's on the market. And most of the cost of making vacuum glass is in the materials that go into it.
I was just thinking about from a NASA perspective or other industries where there would be the need for different composition.
If there were a
of
need
glass.
for different glass, I really don't see a problem. We can weld to tempered glass, for example. I'm sure we could easily weld to other types of glass. The main condition is that, let me explain that glass is mostly oxygen by volume, and aluminum, which is our seal material, loves oxygen. And so the ultrasonic cold welding technique that we use basically breaks up the aluminum oxide on the surface of the aluminum and exposes it to the oxygen bonds that are dangling at the surface of the glass. And as long as that glass has oxygen, we should be able to bond to it.
So your model is a licensing model. So why do you need? And you're not going to do. You're not going to build a manufacturing line. Why do you need $13.2 million?
We believe we will need a manufacturing line. We probably need that first manufacturing line because there's not going to be just one licensee. Right now, simplistically, we divide the world up into 3 areas: the North American market, the European market, and the Asian market. And we believe we're going to need a line ourselves that we can bring people to train them and to get comfortable with the technology, as well as for us to advance the technology.
Okay. What other advances you need?
We think we're.
You already have. It looks like you have a solution, right?
It looks that way, doesn't it?
You tell me.
But we have risk remaining, and we've got a good 2 years of risk remaining. We need to improve the hermeticity of our seals to get to that life goal and work out how we're going to use a getter in order to soak up the residual gases. I think the spacerettes have really come into focus, and the risk has gone way down on those in the last year. But the plasma degassing is another area where we need to reduce the time. As I said, cost is king, and in order for us to really have a market, we need to compete with dual pane. And just to give you a sense of the challenge, the current industry standard for production of dual pane is they can produce 1 dual pane unit every 30 seconds.
So you brought up cost, which so I'll ask another question on that. So I know nothing about glass and the pricing of this. Is there a decline in price year over year, like 5%, 10%? And 3-4 years from now, will you be able to? Will the traditional approaches be cheaper than where you think you will be?
They have pretty much wrung
Or is it
out
saturated?
all of the coast. It's flat. And let me give you an example. I mean, windows have been around for well over a century, and glass windows, that is, flat glass. And float glass process was developed in the 1950s. The low E coating was developed in the late 1970s, early 1980s. That really took off. Over 5 years, it reached 20% market penetration in the 1980s. So these are 50-year-old processes, and they have wrung out as much cost as can possibly be wrung out. We're starting out. We've got a long way down to go, and I think that it's going to take us some time to reach cost parity, but the sooner we can get there, the faster we'll grow. And there won't be anyone, I think, who would continue to use dual pane conventional argon-filled glass once we do that. It wouldn't make any sense.
So I'm struggling just a little bit about switching costs associated with the manufacturing line itself. Can you talk to that a little bit? And it sounds to me like you've got a process. I'm not sure it's a scalable manufacturing process, so maybe you can talk to that. But switching costs seem to me to be astronomical when I think you were trying to get to the why do you need 13 million? It's to create a demonstration manufacturing line, correct?
It's to create what you might call a pilot or a demonstration line that we would use in-house for continued R&D over the years in order to get that cost to keep coming down. I'm not quite sure what other things I can talk about that aren't really proprietary.
So how much of an existing manufacturing line on how much are you changing over? Is it 100%? Is it 50% of the process? I'm just trying to get a sense.
If you want to think about it in terms of percent, I would call 50% a reasonable estimate. I'm a process engineer by osmosis, and in process engineering, you start off with a basic block diagram, and if you block diagram the dual pane process, you get a certain number of boxes, cut the glass, wash the glass, twin the glass, and so on. Our block diagram is almost twice as many blocks as a conventional dual pane system. So for us to compete with dual pane, we're going to have to really focus on throughput. Throughput is going to be critical in order for us to meet that bogey.
So what about vacuum glass manufacturing lines, though? Because I think that's who you're actually are going to be your early adopters of this new technology. Am I incorrect in that?
I'm not quite sure of your question.
So there's existing vacuum glass manufacturers.
There are existing vacuum glass. Their cost and their commercial price is so high that there's no significant market for them except locally. The biggest in the residential and commercial building space is Nippon Sheet Glass in Japan, and they are licensing solder glass seal technology from the University of Sydney that was developed in the late 1990s, 1980s, 1990s. Their costs on the commercial market are about 4 or 5 times higher than dual pane. There's just no broad market for that. You really need even triple pane, which might add another 25, maybe 50% to the manufacturing cost. Only 5% of the US market is triple pane.
How big of windows can you make?
We should, theoretically, we should have no limit. We should be able to make as large a window as they currently make. I think the largest that a residential insulating glass maker deals with is something like 76 by 108 inches.
But the larger you go, the more strain you'll put on your edge seal, right?
And our edge seal will be able to stretch. We're the only company in the world that uses a mismatched seal. And some of you from NASA may have heard of the housekeeper seal, which is a mismatched seal. And what that means is that the metal coefficient of thermal expansion is different from that of the glass. And so the metal needs to be malleable so that it can give, so that the stress of the bond is less than the yield strength of the metal. And that's our philosophy, and we've shown that that works.
And that's time. Thank you very much.